right. Hi, everybody. Hope you're doing well. Let's talk about modern physics. So, maybe you didn't realize this, but everything that we've done in the course up until this point has been what people call classical physics. And this is physics that was basically done between the 1600s, when Newton was alive, to the 1800s, when Faraday was alive. So F equals ma, Coulomb's law, V equals IR, all these things are things that were sort of discovered and published within this kind of time frame. And obviously, there are still physicists, there are still people studying physics, learning new stuff, and there have been people doing that, since Newton's time. So, there's a bunch of other physics that was discovered more recently, like in the last 100 years or so. And everything kind of from that point on is what we consider modern physics. Now, of course there's new stuff, but if you think about it, if it took a lot of smart people hundreds of years to get to the point where they were ready to figure this stuff out, it kind of gets more complicated as you go. So there's a reason that we haven't been covering as much of it, and when we cover modern physics, we're going to describe some of the general ideas, some of the interesting things you can observe, but we're not going to get as deep into the equations as we have been doing, because instead of the equations being like F equals ma, they look more like this. This is the textbook from probably my favorite class that I took in college, which was Quantum Physics 1. And this is the Schrodinger equation. It's a second order partial differential equation, which is a phrase that probably means nothing to you, meaning that you are not ready for this kind of physics. It is super cool and super fun though, don't get me wrong. It's totally worth learning if you are interested in it, but you definitely need to take some more math classes before you're ready to take this stuff on the deeper equation kind of level to really understand where these ideas are coming from. So I'm going to be describing some things to you, and trust me, there are equations to back this up. There are experiments that match those equations, but it's a little bit beyond what we're really able to kind of go through the process of explaining all the math for in a high school level physics class. And even in superphysics, they don't really touch this stuff on the more deeper mathematical level. But it's super cool. So we'll learn about some of the things that are kind of interesting ideas, interesting facts that come out of these crazy looking equations. So there are some limitations to classical physics, and basically classical physics describes things that are easy for us to observe. So it does a good job at this. So things like friction, or static electricity, or even circuits, we can build a circuit and observe things happening pretty easily. But these are things on a fairly large scale, meaning that when we think about an object, we're not thinking about the individual atoms in that object. We're thinking about, okay, this object has a mass of 0.5 kilograms. Obviously, we know that that object is made up of a bunch of little atoms, and each of those atoms has protons and neutrons and electrons, but we think about the object as a whole. So we call this macroscopic, and it just means macroscopic. Objects that are made of many, many atoms, and we think about the object as a whole rather than, thinking about the individual particles within that object. The other things that are sort of part of classical physics are like normal amounts of speed or density, right? Things that we could actually like picture and hold and touch in real life and do things with. The equations that we've learned so far do a pretty good job of describing those things. We throw a ball, we can figure out what's the mass of that ball, what's the force of gravity, how much kinetic energy does it have, how much potential energy does it have. Those are things that are pretty easy to observe and measure in terms of like normal human experience. Modern physics goes a little bit beyond this. And a good way to kind of understand what's going on with this is to think about like a computer image, a digital image. So if you look at a digital image from a distance, it will look like a smooth, realistic picture. But when you zoom in, you see that it has individual pixels. And these might look like little squares, or they might look more like blurry dots depending on how you're viewing the image. And it turns out that these pixels have kind of different rules for how they behave than the larger image. So when you're looking at an image, right, from a distance you see a picture of, a paperclip or a table or a person. You see that as one unified object. But when you zoom in really close, you see that it's actually made up of these smaller pieces that by themselves don't really look like anything. Only when you put them together in a large amount does it really look like anything. And the same thing is true of physics. When you zoom in, to individual particles, for example, electrons, etc., they kind of have different rules than the baseball-sized objects that we have already studied. So the set of rules that really tiny things follow is called quantum physics. Okay, so when you hear quantum physics, it sounds intimidating. The math is pretty hard, but what this word quantum means is basically studying things in small, separate pieces rather than kind of the combined whole object. So studying how does an individual atom interact with another atom? How does an electron interact with a proton on a tiny scale? Those questions have to be answered using different rules than just the equations that we're used to for dealing with large objects. One of the interesting sort of parts of quantum physics is this idea of a photon. So electron, neutron, proton, these all have like this on ending that indicates a particle. And a photon is a particle of light. And you might be saying, wait a second, I thought that we discovered that light is a wave. And that's different from a particle because a wave is just sort of a moving disturbance. It doesn't have a mass. It's not its own separate piece of something. And that's true, but just like when you zoom in really close on an object, you can see that it's made up of atoms. In some ways, when you consider a very small amount of light at a time, you can see that it's made up of photons. So for example, here is an image that they made using different amounts of photons. And you can see the image gets clearer as they increase the number of photons. This first image only has 1,000 photons making up the image, and you can see that it's made up of separate little dots and not a complete picture. So in a sense, the photons almost are like the pixels of light, except that they are a very, very small amount of energy. So the energy is made of tiny pieces. So the equation for the energy of a photon is E photon, meaning the energy of the photon, equals H times F, or H times C over lambda. Now, hopefully you remember that C is the speed of light, F is the frequency, lambda is the wavelength. These are the same letters we've already been using. And this H is a new constant. It's on the front of the reference table like everything else is. H equals 6.63 times 10 to the negative 34. That's a really big exponent in scientific notation. It's the biggest exponent on anything. I mean, it's a negative number, but still. And the units are joules times seconds. These constants often have weird units like this. So let's do a couple of examples to hopefully help you see what the idea is, what's going on. So how many photons per second would we need to make 1 watt of energy in a microwave? Now, most microwaves are like 500 or 700 or 1,000 or 1,100 watts, but 1 watt of energy, how many photons would that be? So 1 watt of energy per 1 second would be 1 joule. Let's figure out how many joules of energy a photon with a wavelength of 12 centimeters would be. So that means lambda is 0.12 meters. C is 3 times 10 to the 8th meters per second. H is 6.63 times 10 to the negative 34 joule seconds. So I'm going to do energy of the photon equals 6.63 times 10 to the minus 34 times 3 times 10 to the 8th divided by 0.12. And I'm going to use a calculator to do this. You don't need a graphing calculator. You can also just type this into Google. 6.63 E minus 34 times 3E8 over 0.12. 1.66 times 10 to the negative 24, and then we have joule seconds times meters per second. Meters cancels out, seconds cancels out. This is just joules because it's an energy. So then we want to know how many to make up 1 joule. So I can just divide 1 by this number. And I get 6.03 times 10 to the 23rd photons. Okay. So in a microwave, there would be like 1,000 times this many photons every second. That's so many. So we don't see them as individual separate pieces because they're so small and there's so many. You could think about it as a really, really high-res image where the pixels are so small you can't see them. But let's take this and let's compare it to light. So how many photons per second would we need to make 1 watt of green light? Let's see. There we go. Okay. So in this case, I'm given the frequency rather than the wavelength. So H is still 6.63 times 10 to the minus 34 joule seconds. And then I don't need C, I just need the frequency. 5.4 times 10 to the 14 hertz. So E photon equals H times F. So I'm just going to multiply these two numbers. 6.63, I wonder if I have it in here as H, probably not. No. .63 times 10 to the negative 34 times 5.4 times 10 to the 14, 3.58 times 10 to the minus 19 joules. Okay? And then how many of these would I need to make 1 joule? So 1 joule, and then I can basically do a unit conversion where I know that 1 photon equals 3.58 times 10 to the negative 19th joules. And so I'm dividing 1 by this number. And I get 2.79 times 10 to the 18th photons. Okay. So let's kind of talk about what we've seen here, because these numbers are really big, they're really hard to picture, or really small numbers, both together. And the concepts are very weird. Here's the idea. You can have 1 watt worth of power made of any type of electromagnetic wave, right? Microwaves and green light, the only thing that's different between them is what the frequency or the wavelength is. Microwaves have a much longer wavelength and a smaller frequency compared to light waves that have a smaller wavelength and a higher frequency. So each individual photon of these two types of waves has a very small amount of energy, but the light photons have more energy than the microwave photons, but they both have a really small amount of energy. You can generally, when you're making an electromagnetic wave, you're making a wave that has a lot more than this amount of energy, and that wave is made up of tons and tons and tons of photons. So we have lots and lots and lots of very tiny amounts of energy making up those waves. And you could have a microwave source of energy that is putting out more power, more energy per second than a source of green light. But the photons themselves, each individual little tiny piece, would have less energy. We're taking that amount of energy, we're breaking it up into even smaller pieces. So you could have a very powerful microwave. You would need to have tons and tons of photons to create that. You could have a powerful light wave, you would need tons and tons of photons to create that. If you're doing something that requires just an individual photon, then the green light photon will always have more energy than the microwave photon. But if you're doing something that has tons and tons of photons, you could have a microwave that's more powerful than a light wave. Okay. It's just a matter of how small of the pieces is that energy being broken up into. And it turns out that when the wavelength is longer and the frequency is smaller, the amount of energy in each piece is smaller. All right. So let's look at some interesting consequences of this. So the first one I want to talk about is the photoelectric effect. And I'll just describe it in words. We're actually going to learn a little bit more about this later. But to help you understand why we care about this photon thing, here's the idea. It takes a specific amount of energy to knock an electron off a piece of metal. And so the electron in the piece of metal is attracted to the positive, nuclei in the atoms of that metal. And it takes a certain amount of energy to separate that electron and knock it off. And it turns out that that because the electron is kind of its own tiny little piece, that all of that energy needs to come from one photon. So you could shine if you shine a light that is a red light, which has a longer wavelength, on a piece of metal, you could shine a really, really bright red light and you could be dumping tons of energy into it. But because the individual photons have less energy, none of the electrons are going to get knocked off. On the other hand, depending on the amount of energy required is different for each material. But if you find a source of light that has a high enough frequency, the individual photons will be more powerful and they'll be more able to knock an electron off of that atom. So to take our microwave versus green light example, if this amount of energy is too small, but this amount of energy is big enough, then the green light will be able to knock off electrons from those atoms, even when the microwave is not able to. They could have the same amount of power, but because the individual photon isn't powerful enough, it's not able to knock off the electron. And then you can do an experiment where you can detect that electron that gets knocked off. So this tells us how much energy is in a photon. We can detect what is the minimum frequency of light that we need to shine that will cause the electron to get knocked off. And that minimum frequency tells us a minimum amount of energy per photon required. Okay, so this kind of concept is called wave-particle duality, because light waves are waves. We know that they interfere in the way that waves do. We know that they can refract like waves do, but they also can be broken up into these separate individual pieces. And it turns out that this is also true in the other direction. So particles such as electrons or even entire atoms can, in very small amounts at small scales, act like waves. So the image on the cover of this book, this right here, is a double slit interference pattern like we've been learning about. And what we talked about with light was, well, we know light is a wave because when we send it through two slits, we get this sort of interference pattern of brighter angles and darker angles. And the red parts represent where there were the most stuff detected. But the thing is, this is not a pattern that they made by sending light through two slits. What they actually sent through two slits to make this pattern was helium atoms. And we know that those are particles, not waves. But we still got this wave behavior from those helium atoms. So waves can act like particles, particles can act like waves, and honestly, when you zoom into these, the quantum level, meaning looking at very, very small amounts of things in physics, the distinction between those two things starts to kind of break down, and it doesn't necessarily make sense to call something just one or the other. We can't neatly separate things into those two categories anymore. So with atom interference, we saw double slit interference with helium atoms. Another cool example of this is the electron orbitals. So if you took chemistry, or if you're going to take chemistry, at some point near the end of the year, you will see a diagram that looks kind of like this. And this is showing you the different ways that an electron tends to hang out around the nucleus of an atom. These different shapes they almost look like bunches of balloons. But what they are is, they're called the orbitals, and they're just different places where the electron is likely to be around an atom. And when they teach you these in chemistry, they're like, yeah, there's these weird patterns, they have this certain structure, there's this many of them, but they don't really explain why. And the reason that they don't explain it is that it's really complicated, but it's also super cool. And you might remember when we were learning about waves near the beginning, we learned about standing waves on the slinky. And you can have this frequency where we have one region where it's moving a lot. You can also have a higher frequency with more energy where it's moving in two regions. And if I can move it fast enough, I could even get 3 areas, although it's pretty hard to do that. And we can create, based on sort of the length of this slinky and its geometry, different types of waves that fit nicely into the slinky. And then you can also move it at the wrong frequency in a way that doesn't really make a standing wave. What these patterns are actually standing waves around the atom. So the electron in an atom creates these different patterns that are actually standing waves with the same sort of different numbers of regions where the wave is strong or weak. And in those regions, it alternates between one direction, which is represented as red, and the other direction, which is represented as blue. And then in between those regions, there's also regions that kind of don't move, that stay at this middle green level. It's pretty wild. So these patterns are called spherical harmonics. They're super cool. You can see that the math is really complicated. Love it. But this is just an example of how an electron, which is a particle, acts like a wave. So an electron in an atom makes a standing wave pattern. Cool. So quantum physics is super weird. You won't have to do too many equations. You will have to do this level of equations, which is almost just like a unit conversion. But it's very cool stuff. It's very weird stuff. It's hard to understand on a deeper level until you have a little more experience with it. But I hope that this introduction to it was interesting and that you learned something from it. And if you have any questions, let me know.